Hello everyone, this is Zahid Kashi. I'm a faculty member in Department of Commerce, University of Gujarat, and a PhD scholar in Delhi College of Commerce, University of Punjab. Yesterday, we have discussed the basic mechanism of uh, descriptive statistic, the correlation analysis and regression analysis. And we have discussed how the Pearson correlation is reported using APA style and how it is interpreted using APA style. Along with this, I have also discussed the regression analysis, the simple regression analysis, the pooled one, using sample pool data of corporate governance and firm performance. And I have discussed how to report the data using APA format and how to interpret that data. Yesterday, I have also discussed using a eye view of assumptions of regression, but today I will discuss in detail what is linearity between independent and dependent variable, how to test the linearity of the variables, and how to test the significance of outlier, how to test the heteroscedasticity, multicollinearity, normality of residues, and how to test the autocorrelation or serial correlation in case of time series data. So we are going to discuss these things in greater detail. So let us first discuss the linearity between independent and dependent variable. You need to understand that linearity is basically the linear relationship between dependent and independent variable, which is indicated by a straight line. So when a linear relationship between independent and dependent variable is indicated by a straight line, that is basically the linear relationship that indicates a linearity. So according to this assumption, there should be a linearity between dependent and independent variable. It means if the relationship is indicated by a linear line, then we can consider it as a linear relationship. But if the relationship is not indicated by a linear or straight line, then we cannot consider it as a linear relationship. Sometimes a curve relationship is there, sometimes a parabola relationship is there, but we need to understand that according to that assumptions, there should be a linear relationship. So first thing that we need to do is we need to consider a scatter plot using Stata, where we can plot the dependent variable against your independent variable. You can then visually inspect the scatter plot to check for linearity. So let's check for linearity of our different variables. So let's suppose I have shared some data yesterday. I am going to use the same data for testing this relationship. I'm going to open the Stata program, Stata 64, for Stata version that we are currently using. Now I'm going to use the same file that I have used yesterday for our analysis. And I have shared this data set, CG data.dda. You may have this data set with you. So what we need to do to consider the linear relationship between IV and DV. So first we need to write here scatter, SCATTER, scatter. Then we need to write the dependent variable. For example, Tobin's Q. Tobin's Q is our dependent variable, and our first independent variable is PR on. So first you click the dependent variable, then you click the independent variable. That is the pattern which I have mentioned here. DV, then IV. You cannot put all the IVs all together. You can test it one by one. So you can use the same dependent variable each time, and you can change independent variable each time. So you need to see the relationship, press enter, and you will see the scatter diagram between both of them. You can see here the scatter diagram. It is not showing any direction here. Uh, it is something like positive, but it is scattered here. We cannot confirm whether it is a linear relationship or not. So how can we confirm whether it is a linear relationship or not? There are some things that we need to understand as a part of linearity. If the relationship displayed in your scatter plot is not linear, you will have to either run a non-linear regression analysis or transform your data. It is basically a remedy. I will let you know how to transform your data. There is a technique which is known as ladder and ladder technique, which will let you know how you can transform your data. So I will let you know. So there are two ways. If your scatter plot shows that there is no linear relationship, there are two ways that you can tackle this kind of data. Either you need to run a non-linear regression, or you can transform your data, which you can do using this data. So I will let you know how to transform the data. But first, let us see how you can use another command to verify the linear relationship. The command ACPR plot, augmented component plus residual plot, provides another graphical way to examine the relationship between variables. So it does provide a good testing for linearity. So this one is a very good testing technique, because in case of scatter plot, you cannot determine clearly whether there is a linear relationship or not. So you need to run this command after running the regression. First, you need to run the regression. Let's suppose this is our dependent variable, this is our independent variable. So first I need to run a regression, right? uh, Dobbin's Q as a dependent variable and PR ownership as a independent variable. So first I need to run the regression. After running the regression, what is the next thing I need to do? The next thing that I need to do is I need to consider this command. So ACPR plot with first independent variable. ACPR plot with first independent variable. First independent variable is PR ownership, which I have used as a independent variable. Then you put comma, then low s. Check the spelling, low s. All right, the spelling is okay. Then you need to press enter, and you will see a command like this. You will see a graph like this. There is a line. It shows some linearity. It is a straight line, although, but we need to verify it further. The option lowest locally weighted scatter plot smoothing draws the observed pattern in the data to help the identity of non-linearity. So you can assess here the linear relationship. You can assess here that a straight line is drawn here. So whenever you observe a straight line, it means there is a linear relationship. So we can test linear relationship on other variables too. Like we can run the regression with dependent variable Dobbin's Q with independent variable 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are basically the total independent variable set that we have with our first dependent variable. So let's suppose that we are going to run this command with this. So as a first step, I have run the regression. Now, as a second step, what I need to do, I need to put the ACPR plot cron. I need to replace this with the second independent variable, which is institutional ownership. And okay, it will generate another one. So this is also somewhat uh, this is also somewhat linear. So linearity may be confirmed by two ways. The first method to confirm the linearity is by seeing the p-value. If p-value here is significant, it means there is a linear relationship. You can observe that uh, PRID is not significant. So let's test this variable with our ACPR plot. So let's suppose I would like to see whether this is indicating a linear relationship or not. So in the regression command, we have observed that PRID is not significant. So let's see whether it is linear or not. So PRCID, yes, this one. Now let's see. You can see here how the values are scattered here. It is showing all the values on zero. This is a straight line, but this is slightly not a straight line because all the values are in the middle of some values and it is upward. Some values are downward from the zero. These are going to the negative side from the middle of the data. So this indicates a non-linear relationship. In the same way, you can observe it on another, that is S growth. S growth is also indicating a non-significant relationship. You can run the same command here. Now replace the variable name with S growth. So S growth is here. Now run the command and you will see a linear relationship like this. No, this is non-linear relationship actually. So whenever you do not find your dots on the straight line and there is a straight line between the variables, it becomes a non-linear relationship. Technically, if you want to understand it, I would like to show you some graph on the online. What do we indicate by a linear relationship and what do we indicate by non-linear relationship? Linearity. Let's go to the images. Now, this is perfect linearity. When you find a picture like this in a graphical view, this becomes a perfect linearity. This is basically something that we want to discover. It may be from lower to upper side or from upper to lower side. It should be a straight line like this. This is perfect linearity. In other cases, there might be some imperfect linearity. This is also a linear relationship, but this is not a perfect one. And what we have indicated in our graphs that were also not perfect. So non-linearity arises when we do not have a straight line. Non- So in case of non-linearity, what kind of graphs we may have? We may have a graph like this which is not straight line. So whenever you might have a curve graph, or you can say which is not a straight graph, then it is become non-linear because in case of linear relationship there should be a straight line. It may be a straight line with some weak fit line. So in this case it is also not linear. If you see an orange line here, it is a straight line. The orange line indicates a linear relationship, but the red line, the purple line, the blue line, they are not linear. So whenever you observe a linear line or a straight line, it becomes a linear relationship. So in case of this, there is no linear relationship because you could not find a linear relationship here. But in case of, for example, institutional ownership, if we observe the institutional ownership here, I would like to show you. You find a straight line, the line like this. This is a straight line. This is not a curved line. So you can observe here a linear relationship. In other cases, like for example, we have observed PR ownership like this. You can put it here, and we will find here another straight line. So this is straight line, and this is not a curved line. So this one is a straight line. So you can observe here a linear relationship. So whenever you find a straight line, whether it is going from the middle to the upward, or maybe from here to here, it becomes a linear relationship. So this is how you can test the linearity of your data. But let me tell you, if your relationship could not be found linear, what to do next? There is a technique which is known as ladder and ladder technique, that I will let you know in the next session, when I have the remedy session. Because today I am going to discuss only the assumptions, that how to test the assumption. There is another file I will share with you to how to test the other assumptions of your data, and along with that, I will let you know how to transform your data if it becomes non-linear or any other assumptions which is violated here. So next we need to understand the assumption two. There should be no significance outliers. That is the assumptions that you need to meet. So there should be no significant outliers. What are the outliers? Outliers are simply single data points within your data that do not follow the usual pattern. So whenever your data does not follow a usual pattern, it indicates an outlier. So always remember, there should be no significant outlier. It means the value of the outlier should not be significant. The p value of it should not be greater than 1.96. The p value should not be less than 0.05. So if there is an outlier and it is not significant, there is nothing that you need to worry about. But if there is an outlier and it is significant, then you need to worry about it, because you need to delete, either delete those outliers, or you need to handle those outliers with that. For example, the problem with the outlier is that they can have negative effect on the regression equation. So if outliers are present in your data, it your it may form your data or your equation, invalidate your results. So always remember, you need to test whether there is an outlier in your data. So prediction value become also not valid. So this will change the output that Stata produces and reduce the predictive accuracy of your results. So in case of outlier, what you will face, in case of outlier, there might be a negative effect on regression equation. What you are expecting a positive impact of a particular variable, and it shows a reverse effect or negative effect, or it may be insignificant, or the predictive accuracy, which means the R square value, may reduce. Fortunately, you can use this data to carry out case-wise diagnosis to help you detect possible outliers. To check for outliers, we use the AVP plot command. So this is basically the command which you are going to use with uh, your your data in order to find out the possibility of outliers. So what is the procedure? First, you need to run the regression. Then you need to write ABP plot. If the t value is less than 1.96, then there is no significant outliers. But if t value is greater than 1.96, there is significant outliers. So in that case, the assumptions violate, and we need to manipulate the data set. I will let you know how to manipulate the data, but first we need to test it. So what we need to do, we need to run the regression first. Each time whenever you apply a different procedure, you need to run the regression first. So let's suppose this is our regression, and this is we are going to run again. Now the regression is run. The second thing we need to do is AV plots. AV plots. So AV plots. Just press enter. You don't need to put any variable name here. If you put a particular variable name here, it will display the AV plots of that particular variable. But if you do not, if you do not put any variable name here, it will generate the AV plots for all the variables. So you can see here, yes. Now you need to see the p-value of each variable. Here t value is equal to 1, here t value is equal to 2, t value is equal to 5, t value is equal to 2.83, t value is not visible here. So if you want to make them visible, some of the t values are here, which are visible. Some of the t values are not visible. So let's suppose I would like to see the AV plot for this first one. Wireless not allowed. All right, they do not indicate the wireless. It's mean whatever they have displayed, they will consider, we will consider it. So let's suppose this is the wireless that we have used with the previous regression. So let me check what the values are there and how there are different types of variables here. So first you need to understand uh, the outliers. Those values which are away from the center or from most of the values are outliers. There are two outliers. There are only two outliers. It's mean two data points are away from majority of the data points, and it is not significant. It means we don't need to worry about this. In the second case, in institutional ownership, you can observe there are only two values which are away from the central data point. So if your outliers are less than 5% or less than 10% in some cases, but less than 5% of your total values, then you don't need to worry about them. But if they are more than 5% of your data set, for example, we need to see how much values are here in our data set. We need to see the data points here, and we need to see how many observations are there. So there are 1955 observations. If we take 10% of these observations, it becomes 195. And if we take 5% of these observations, it becomes almost 95, almost 95. So in our case, there are less than there are less than 5% because only two values indicates outliers. So it is ignorable in all cases because there are no outliers in most of the cases. Only two or three values are there you can observe as a outliers. In case of variable s growth, there might be more than that, but that is not linear relationship. So in our case, it is ignorable. There are significant outliers, but they are less than 5%. So whenever your outliers are less than 5%, it means that you can ignore them. You can continue your regression. You can estimate your regression. But if your sample size is too much small and more than 5% data points are indicating as an outlier, then you need to be worry about it and you need to manipulate your data. So I hope you have understand this point. So the next is assumption number 3. There should be homogeneity of variance. Homogeneity means constant. The variance across different error terms should be constant. So the error of variance or variance of error should be constant on each observation. Your data needs to be your data needs to show homoscedasticity, which is where the variance along the line of the best fit remains similar as you move along the line. So this is basically a favorable condition. If your data shows homoscedasticity, it means your assumption number 3 is fulfilled. But if your data does not show homoscedasticity, it means heteroscedasticity, which is the violation of assumption number three. So if your variance along the line of the best fit does not remain similar as you move along the line, it becomes heteroscedasticity, which is violation of the assumption. So we assume that there should be absence of heteroscedasticity. So what do you mean by homoscedasticity? Homoscedasticity means equal scatter. It means there should be equal variation along your regression line. While heteroscedasticity means unequal scatter. Hetero mean unequal. Homo mean equal. Sedasticity mean variance. So when there is a equal variance, it means equal scatter. It means homogeneity of variance, which is the fulfillment of assumption number three. But when there is heteroscedasticity, it means there is unequal variance. So it becomes heteroscedasticity. In that case, our assumption is violated. So what causes heteroscedasticity? How heteroscedasticity becomes in your data sets? So heteroscedasticity is mainly due to the presence of outlier in the data. So if your data has some outliers, it means there is a possibility that your data may have heteroscedasticity, because outliers basically indicate some heteroscedasticity in the data. So it is possible, if there are some outliers in your data, there might be some heteroscedasticity in your data too. So the outlier in heteroscedasticity means that the observations that are either small or large concerning the other observation are present in the sample. Heteroscedasticity is also caused due to omission of variable from the model. Sometimes we may omit some important variable in the model. Like if you see our model, there are some variables which are located here, but our R square is very small. If the R square is small, it means we need to include some important variable, and we need to exclude some of the variables we have included here, which are useless. So most of these variables are not explaining the dependent variable. That's why your R square is small. So whenever we have omitted some important variable from the model, it may be possible that heteroscedasticity is there. So a classical example of heteroscedasticity is that of income versus expenditure on meals. As one's income increases, the variability of food consumption will increase. When your income increases, you may try to eat junk foods like burger, like shawarma, like pizzas. You may try to increase the consumption on those food items. Those with higher income display greater variability of food consumption. Some may have some may consume less food. Either their income is increased or decreased. Some may take more junk foods. So the variance of error may increase with explanatory variables mean independent variables. Subpopulation may have different effect if your population may have different category. For example, I am doing a research on listed companies of Pakistan. And as we know that listed company of Pakistan may have different subgroups, like some of the listed company may be from banking sector, some of the listed companies may be from manufacturing sector, some of the listed companies may be from cement sector, some of the listed company may have from communication sector. So when there is a subpopulation within your target data, then there might be different effects. In that case, there is high chances of heteroscedasticity, because each subpopulation may have their own characteristics. There might be measurement error. Sometimes the formula that we are using for measuring our independent variable or dependent variable may have some error. In that case, there is a high chance of heteroscedasticity there. there might be wrongly specified model. It may be possible that your data requires to apply a time series model and you are applying a pooled model. Your data is requiring to consider a panel model and you are applying a cross-sectional model. So if you have wrongly specified your model, in that case, heteroscedasticity may occur. In the other way, missing values or missing variables, like I have told you, that sometimes you may have omit some important variable from the model that should be included here. So if you miss some important variable, it may be a chance that heteroscedasticity may arise. Heteroscedasticity is more likely in cross-sectional data due to heterogeneity of groups. Heterogeneity means when you have subpopulation, when you have different groups in your population. So the data that you have collected from different companies, if they are divided into different groups, then there is a high chance of heteroscedasticity. So in case of cross-sectional data, there is high chance of heteroscedasticity. Different quality of data. If your data indicates different quality, some of the variables are qualitative, some of the variables are quantitative, some of the variables are discrete, some of the variables are continuous, some of the variables are nominal, ordinal, or scale variables. So whenever your data indicates different quality, it may also indicate heteroscedasticity. So always remember these points, that may be the reasons why your data indicates heteroscedasticity. Then time dependence of the variable. Sometimes you are using a pool data set, but it is actually a time series data set that you need to understand. So if the data shows time dependency and you are not using a time variable with that data, in that case, it will show heteroscedasticity. Now, what are the consequences of heteroscedasticity? What will happen if we ignore the heteroscedasticity and we do not remedize heteroscedasticity from our model? What will happen? What will happen with our results? Whether our result will be valid or not? Can we interpret those results? Can we create the implications? Can we create the prediction on those results or not? Can we make decisions on the basis of those results or not? So always remember that the OLS estimators and regression prediction based on them remain unbiased and consistent. So if you are using OLS model, and you are just predicting your data, it's mean you are not testing any theory, you are not testing any hypothesis, you are just predicting whether it will increase your dependent variable or it will decrease your dependent variable. Then in that case, you can ignore the heteroscedasticity. But the OLS estimator are no longer blue. What do you mean by blue? Blue means best linear unbiased estimators. So in case of heteroscedasticity, your OLS estimators means beta coefficients. The betas or coefficients that you estimate from your regression analysis, they becomes no longer blue or best linear unbiased estimator because they are no longer efficient. So the regression prediction will be inefficient in that case. So OLS estimator remain unbiased and consistent. However, the distribution of estimator is affected, increasing the variance, because in case of heteroscedasticity, the variance will increase in your data. So your estimators becomes inefficient. Your minimum variance property is violated. In that case, you cannot make any decision on the basis of those coefficients. If your data has heteroscedasticity and you have estimate some beta value and you are going to interpret that with the increase in A, B will increase by this value, this is invalid interpretation because heteroscedasticity is there. So always remember, whenever you find heteroscedasticity in your data, you need to remove that heteroscedasticity before making any interpretation or making any decision. Next is estimate of variance are biased. So whatever you basically uh, estimate in terms of variances, it becomes biased. You need to change the formula. The standard error, the confidence intervals are not correct. Yesterday, I have shown you a regression analysis without robust command and with robust command. So with robust command, their standard error basically change and they are corrected. And without robust commands, the standard error are not valid. So in case of wrong standard error, wrong conclusion on TNF, because T is calculated on the basis of coefficient and standard error. So if the standard error are wrong, it means the T are wrong. And if T is wrong, the F is wrong too. So we cannot interpret them correctly. Significance test too high or too low, there might be chances that you find the p-value higher than the actual or lower than the actual. So you need to rectify the standard error order to make your uh, t-value or p-value comparable. OLS gives more weight to larger error, minimum sum e square. So if HSK is there, then overemphasize extreme value. So in case of OLS, it will consider the larger error and it will ignore the smaller error. It means whatever the value you takes as a beta coefficient from the OLS, it will not be valid value for the interpretation. So extreme values contain less information, so should be given less importance. So always remember, whenever you find heteroscedasticity in your model, always try to remove the heteroscedasticity using robust command. Otherwise, you cannot make any decision. You cannot interpret your coefficients. Your interpretation may not be valid for that specific coefficient. So what we need to do, how to detect heteroscedasticity, how to find whether there is a heteroscedasticity in our data or not. There is less than 1 minute finishing the meeting. Please use the same link that you have used for joining this meeting to join again, so that we can start from here, from detection of heteroscedasticity. Join again from the same link so that we can start over again from the detection of heteroscedasticity.